we're very happy to have Fernando Tohme telling us about a categorical treatment of economics.
Thank you for inviting me. It's a pleasure for me to be here, and I want you to stop me at any point if I'm mistaken or saying it wrong, because you remember I'm an economist, not a category theorist. But I really love category theory, and I think that it should be incorporated as a tool, but also as a way of thinking into social sciences, in particular economics. Let me start saying what's economics. The usual definition is due to Lionel Robbins, a British economist of the 30s, who said that economics is the science which studies human behavior as a relationship between ends and scarce means which have alternative use. So you have this definition in its British gloriousness, but the point is that it puts at the same footing ends and scarcity. That means that a scarcity, the idea that there is a resource that is not enough, is as much as important as the ends, the goals of individuals or entities that could be companies, firms, governments, and so on. But then I ask, would economics disappear in a world like Star Trek, in which you can have a machine that makes everything you need? And this is an interesting discussion, and there is an entire book on this subject, but I think that focusing too much on scarcity is misleading. I think a more general definition of economics is that it's the study of the interaction among intentional entities. Of course, other social scientists resent this definition because it also covers sociology, political sciences, etc., etc. Even ecological studies or some branches of biology. But I think that economics has the right intuitions to focus on this, on the interaction and the intentionality of the agents. So if that's the real goal of economics, the question is why should we use a categorical treatment, since there is already a whole toolbox of mathematical methods used in economics, ranging from calculus to linear algebra, from functional analysis to algebraic topology, which are used in very elementary ways, but still used there. So, but we find that category theory provides tools in which different goals really matter for the question of what's the outcome. So, sorry. So here I want to address this question, in particular the impossibility of separating local interactions from larger interactions. This is something that economists always use by applying what is called the ceteris paribus condition, which means that everything remains equal, we only focus on this. But that's not a real phenomenon. It must be really independent to apply this kind of analysis. So I will start talking of an instance of this problem in which I went to try to see if the very notion of agent is well defined. And the answer is, well, agents can be complicated entities and not the simple ones that are assumed in economics. And the other one is to see if interactions among different entities, as I said, could be companies, governments, individual agents, and so on, if that scales up when we aggregate them, when we put them together. And in both cases, I think that I can apply an expression, a couple of expressions that I learned from one presentation by David, which is the level agnostic and or continuous with respect to subagents. I think economic theory must adopt this point of view, must be level agnostic and must be continuous with or continuous with respect to subagents. So the first problem, the problem of agents, of what an agent is. In mainstream economics, we say that an agent is fully described by the preferences the agent has over a set or space of alternatives. And the agent is said rational if he chooses or she chooses the most preferred alternative among those that are feasible. But behavioral economists, which is another branch of economics, weakened this definition and allowing the agent to choose what it seems to be the most preferred alternative, given that, so for instance, if you go to a restaurant and the menu is very, very long, you just stop at some point and say, well, this is enough and I will pick up this dish, instead of looking at the entire set of possibilities. But in applications, and most applications in economics, are concerned only with some subsets of the entire space of possible alternatives. So, for instance, if I describe myself, I have preferences over traveling, reading, eating, etc., etc. But in those studies, they focus only on one of those problems and leave the other like fixed. Like I said, the ceteris paribus condition. But this requires to assume that the preferences are independent on each of these sub-problems. So, without saying that, in economics we speak about local problems. So a local problem will be kind of a subset of a larger problem, and there will be a preference represented by a utility function that is the restriction of the global utility function over each problem. Now the question is, are we able to recover the global preference, the global utility function, just from analyzing the behavior on each of the local problems? And so let me analyze that problem, because I will, and I anticipate the final answer. We cannot ensure the consistency of this gluing of local solutions to yield the whole picture. And if that's right, that would mean that at each problem, agents become other kind of agents, kind of a different agent interacting here instead of here, and it will be a difference between them that cannot be seen as the projection of a larger preference, of a larger a goal in terms of a single agent solving all the problems she has in life. So we start considering a class of a space of possible options, of which one must be selected, or some of them must be selected, and the selection is made by evaluating a utility function. And having constraints gives us a restricted set of possible alternatives. So for instance, if I want to buy a car, I cannot buy a Lamborghini because I don't have the money for that. So I have a restriction, but I can choose inside that restricted subset. And I will find a global solution there. But now consider the sub-problems, the local problems, and we have a family of them. For technical reasons, usually those sub-problems are described in terms of being choices that have been made in closed linear subspaces of the entire space. So if we have a global optimum, then we can project it over each of those subsets, subspaces. And this projection gives us the closest we can come in that particular problem to the global solution. But sometimes our projection is not exactly one solution that can be found in that restricted subproblem. So we can define what of those solutions in the local problem are closer to the projection of the global solution. So it doesn't need it to be the same thing, the solution in the local problem and the solution in the global problem. But if we project the global problem into the space, the subspace, we want to find the closest we can come to that. So we can define what a local problem is, and we will have the subspace, the restricted subspace of real possibilities, we have the restricted utility function, and we have the choices that can be made according to that local utility function. And here comes where I think that category theory can be useful. I think that we can create a category of local problems and assume for simplicity that each object will be a local problem, and assume that a morphism will be saying that if I have a problem Sk, the problem Sj in its codomain will be a larger problem in which the local problem has a utility function that is the restriction of the larger problem. And well, we can show that the composition exists, it's associative, and so on. So it's a very trivial category. But we can also define another category in which the objects are subsets of the entire space, and the morphisms are composable correspondences. Correspondence is in economics is used instead of multi-valued function. But the idea is that you don't need to assign a single entity to a single one. You can have one to many, right? So we can define a functor from the category of the local problems into the class, or the category of those subsets. And it assigns to each problem for instance, if I have problem sk, it sends all the objects, all the alternatives in the space that, when projected, give us an optimal level, optimal value at the local space. So we can see here that if L is the entire space, Lk is one, suppose it's one of its subspaces, and I have a restriction, Lk hat, then I find the optimal values here, and then my functor sigma assigns to the problem those alternatives that projected give us back the optimal values in the subspace. Oops, sorry. So, well, a section sigma of this functor gives us these elements associated to a local problem, and given two problems, Sk and Sj, we note by the definition of the morphism that actually Sk, if I have a morphism Sk to Sj, it means that Sk is a restriction of Sj. So I have a problem, a larger problem, of which this one is a restriction. And then the correspondence, the morphism should be such that if I take the larger problem Sj, project its solution on the K space, and then go back to the entire space, I recover the alternatives in Sk. But you see, the morphism goes from the Sk to the Sj problem, while the functor sends us from Sj to Sk. So it's contravariant. So the idea is that we can find several local problems, each one with its optimal values, and then we go up to the entire space. We have the corresponding sigma values that projected back give us the closest we can to the optimal local values, and we can see that they might intersect. And so the question is, will this give us a gluing of the local problems to recover the global one? So in more technical terms, the question is, does this constitute a sheaf or not? So I have an example. I don't want to elaborate much, but suppose that L is the entire three-dimensional Euclidean space. I have a utility function there, and I have a single global solution. Then I have two subproblems, one of which is the xy plane. And then if I restrict the utility function to this space, it gives us two solutions. And then I have another problem, which is that the subspace I consider is that subspace of R3 that is perpendicular to this vector. And when I solve the system, when I find the optimal values, I have these 2 points that are symmetrical, right? So when I project the global problem down to each one of those, the closest I get are exactly, remember that gamma, gamma gives us the closest optimal solution to the projection of its argument. So if I project 0, 0, 0 on the xy space, and I have two solutions, 0, 1, 0, or 0, minus 1, 0, both of them will be at equal distance of the projection of 0, 0, 0. So both of them belong to gamma 1. And the same thing happens with gamma 2. So, but now if I add a new problem, which is the optimization of U over the surface of the three-dimensional sphere, I get again 0, 1, 0, minus 1, 0 as solutions. Now I have three problems. Sorry, I will add this. I have three problems, S0, S1, and S2. And I have these four solutions. And I can see that S1 and S0 yield the same solutions, while S2 has these two other solutions. But we can check that each one of the S1 and S2 problems are restrictions of S0. Why? Because each problem is a each one's S1 and S2 are problems of maximization of the U function restricted to subsets of this S0 problem. And on the other hand, when we apply our reconstruction correspondence, if we are given S0, we project it over each one S1 or S2 and then go back, we get the local sections of the problems S1 and S2. So the idea is that if I have a larger problem Lj, a smaller one Lk, one Lk is the restriction of Lk, I have the solutions corresponding to the solution of J, and here the solution of K, then I can reconstruct the solution of the smaller problem by applying this back and forth projection on the solution of the larger problem. As I said, the sigma is contravariant, so it's a presheaf, and we can also see that each of the smallest problem can be seen as covering the global problem, because we can reconstruct getting the union of all the the spaces of the subproblems, and the problem of the space of the global problem is included here. So, and we have this definition of compatibility of those sections, of the solutions, the epsilons, and it should be that they are coincident on when they are projected back either on the K is projected to K and L, or when the L problem is projected over K and L. So these are conditions for a sheaf, right? Because we want to see if sigma is a sheaf or not. We know it's a pre-sheaf, but we don't know if it's a sheaf. But the condition for the existence of a sheaf is that each local section is the global one intersected with the projection back to the larger space, to the global space of the solutions of the K problem. So it will be a sheaf if I can do this with each K sub-problem, each K local problem, then I can reconstruct the entire section for the global problem. In our example, actually this is easy because they don't have common problems, so it's trivial and it's a trivial sheaf. But it was just in order to show that it's a numerical example that helps to illustrate this. But in general, we can ask ourselves if this condition is satisfied in every possible case. So notice that this sheaf condition indicates that the solutions of each of the local problems are not contextually dependent on the solutions of other problems. It just must be coincident, but it doesn't, information of the other problems is not needed to solve this problem, a particular problem. But then, if you consider a different sequences in which a same problem can be solved, say by using the information of previous cases, this is what is done in what is called it's a technical name developed by two Israeli economists, Itzhak Gilboa, David Schmeidler. It's called case-based decision making, in which you use previous cases to solve new cases. So in that framework, the path of previous problems solved change the solutions for a single given problem, even if it's the same problem, because the past can be different, and so the choices you made will be different. So the solution, it depends locally on the past, the path of previous problems solved. And, oh, sorry, yeah. So let's see the conditions that should be satisfied to be a sheaf. And so the question is, if I have the maximizers of a local problem, I want to glue them together and see if I can recover the global solution. So I define for this lambda mapping that actually sends us from a given set of possible outcomes, which problems could be solved by them. So if I have a set X of candidates to be solutions, I project them on each of these subspaces, and if this projection coincides with the solutions I already have, then I say that these three problems belong to the image of lambda. If there is another problem in which the projection is different from the local solutions, then that problem cannot belong to lambda x. And it's easy to see that if I have the solution of a problem S, S should be in the image of lambda sigma S. That means, going back to the previous figure, if this is sigma, the solutions of a problem, say 2, of course, when I project it, it will give us the solutions here. And so this problem will belong to the image of lambda. So this will happen always. But the real problem is to show the other way around, showing that if I have the projection, the solutions of problem S, when I project that, I get exactly the problem S. That this is the solution of problem S. And the fact is that this gives us lambda as a fiber bundle. And it will be trivial with a fiber that gives us the global problem. The only problem that matters will be the global problem. So I know that this will happen, which we are interested, this equality, if and only if there exists a global utility function such that each of its restrictions gives us the same points. Well, sorry, there exists a local utility function that is equal to the restriction of the large U. So it will be a trivial bundle only if there is a single utility function and every problem is actually the solution of a restriction of that large utility function. But if the problems have different U's that are not restrictions of the large U, then I cannot make them compatible. There will be no sheaf condition. It will be not only a trivial bundle, but it won't be a sheaf. And so this shows, and there are so many examples of this that we cannot ensure that there exists a single agent that behaves consistently at each of the problems the agent focuses on. So this is a main problem, because mainstream economics assumes, without saying, that lambda is a trivial bundle, so that it's consistent. But as I said before that, prospect theory by Daniel Kahneman and Amos Tversky shows that it depends on the reference point in which a problem is solved. If you paid for a ticket and you lost it, you will regret it in a different way if the ticket were given by you as a gift. And so the reference point, the point from which we depart, will lead you to make different evaluations of the same outcome. And that means that this lambda cannot be trivial, because the decision is made with respect to context. It depends on other problems, on other aspects of the problem. And as I said, the case-based decision theory assumes that the similarity to previous problems leads you to different solutions. And again, lambda is not trivial. So there is no way in which we could make consistent different views of economics. The mainstream one, the one given by prospect theory, this case-based reasoning one. So there is a multiplicity of possible models of economic behavior, and all of them differ in what an agent is and how an agent solves a particular problem. So there is no unifying view. Now let's scale it up to the interactions of agents instead of a single one. And the interactions in fixed patterns is called a game. An interaction in a fixed pattern is called a game in economics. But the question is, can we connect games such that players can change the outcomes in another game, behaving differently in the first game or not? So this is an open question for which there are very particular solutions given, but not a general one. Open games addresses this issue by using the concept of lens, the idea that you can connect two games, but the results of the following game must affect in some way the previous game. Here we will do something different but related somehow. And here we will consider the notion of a game in which we have players, we have strategies, we have outcomes, this is very important, and we have a payoff, a relation between the strategies and the outcomes. This is important, the distinction between outcomes and strategies, because we want to preserve the idea that agents can reason backwards, considering what outcome they need to do something in the following game. So we will have a morphism between two games if the agents of the domain game are players also in the other game. We have that the strategies of this game are strategies of this game, but the outcomes of the larger game are included in the smaller one. And of course, the strategies in the larger one can be projected on the strategies in the smaller game. The idea is that I can look forward from a sub-game to a larger game, but the larger game actually influences the decisions to be made in the smaller game. This is not a lens, but it it shares its flavor. This is very well known in the literature on game theory done by Soviet mathematicians, interestingly, and it has been kind of lost on Western game theories. But this idea of the back and forth connection is necessary. So if I create a category in which the objects are games and the morphisms are that, we can prove that it has finite colimits. There is, of course, the initial game, and of course we can define co-products as direct products of games. But then, and this is something we discussed years ago with David, we can define cospans in the category with finite colimits. And so we can create or can work in a category of cospans. That means that the objects are games, but the morphisms are now cospans. And we can make this a monoidal category using the coproduct as the tensor product in the monoidal category. And then we have this monoidal symmetric category of cospans of games, and we have a morphism can be defined in terms of a cospan. But it's interesting that when F and F bar are isomorphisms, we can say that G bar is actually the minimal game that includes all of them as subgames. And then we can work on the framework created by Brennan and see it as a hypergraph category. Let me skip the part of the Frobenius properties, but they can be checked that they work. And but the interesting thing is that we can define a mapping, and actually it's a functor ec that sends to each game to each class of equilibrium strategies. And we can define an operation that, given two equilibria, will give us an equilibria in a new equilibria that belongs to the class of equilibria created by this operation. And this operation must be such that if I have a player that plays in both games, then the new strategy must be a combination of the strategies used in one game and in the other game. And that means that it obtains, this is the product, it should be the co-product, the sum. It adds up the payoffs he received from playing in both games. And players that play just in one game that receive the payoff of that single game. So we see that if we define this operation, the class of equilibria that we obtain is the class of equilibria of the co-product of the two games. And this shows that this ec is a lax monoidal functor.
Doesn't it show it's a strong monoidal?
Sorry?
Doesn't it show it's a strong monoidal functor?
Yeah, of course, but I prefer to be cautious. Yeah, you're right. If I use equality, it's strong. But for me, it's enough if it's lax, because it means that it preserves the equilibria. So consider two famous games in the literature. One is called The Battle of the Sexes, husband, wife. It's a game created in the 50s, so sorry for this. They have to decide if they go together to box or to ballet. They don't want to go to different venues. So 0 is the payoff for both in those cells that mean that one goes to box and the other to ballet, or vice versa. But if they, this is wrong. Should be at 2. If they go to box, the husband is happier than the wife, but she's happy of being with him. If they go both to ballet, the wife is happy, and the husband not so happy, but it's still happy for being with her. On the other hand, we have another game called the Prisoner's Dilemma. We have two prisoners. They are interrogated together, and they can help the other one by remaining silent, or they can betray the other. If they cooperate, they receive a payoff of 2. If one cooperates, remains silent, while the other betrays him, the traitor receives 3, that is more than 2, but the one that remains silent gets 0. The other way around is this payoff, and if both betray the other, they get 1 each. In red, I marked the Nash equilibria. The strategic situations in which no one of them has incentive to move out, to deviate from that. This is the standard of potential prediction in game theory. Of course, in the Battle of the Sexes, we have 2 Nash equilibria. So what's the recommendation for each player? You don't know, because one might think that the recommendation is to go to box, and the other can think to go to ballet. So it's not a prediction of the outcome of the game. It's a description of what are the strategic incentives of the players. Now, you can see here that I have player 2 playing the box ballet game, but plays also the Prisoner's Dilemma. So if I wire them together, I get a larger game, which I call Battle of the Sexes plus Prisoner's Dilemma. And the idea is that the inputs come from the strategies used by the players, and the outcomes are the real outcomes of the interaction, right? And so we can write down the large matrix of this co-product of games, and then we will have 2 matrices. One corresponds to player 1 choosing either box and ballet, player 2 using box in one game and cooperate in the other, box in one and defecting in the other, blah, blah, blah. And we have the third player, player 3, choosing the matrix, choosing if the third player plays the Prisoner's Dilemma. So this table corresponds to playing cooperation. The next table corresponds to choosing betraying the other. And the payoffs, you can see here, the players that play only one of the games preserve their payoffs, while the player that participates in both receives the product of those in those games. And we can calculate the Nash equilibria, and the Nash equilibria are these two, meaning that player 1 should go to box and player 2 to box, while player 3 should go to should defect and player 2 should defect. And the other equilibria is that player 1 should go to ballet, player 2 should go to ballet, and player 3 should defect. So it merges the two equilibria. But then, very nice, we have composition and we have a tensor product, but it's too rigid to capture the dynamic of economic interactions. In this example of Battle of the Sexes and this prisoner's dilemma, the very interaction among them should change a little bit the payoffs they receive, how they evaluate the results. So we need a more flexible structure. And a possibility is to consider an org-enriched dynamic category. And, well, this will be for you like a description of what I understood of your framework, which is the idea that org is a bicategory where the objects are polynomial functors. Morphisms are the categories that are for given two polynomials, PQ coalgebras. And since this is an internal home in poly, we can see this as a process that takes outputs of P to outputs of Q and inputs of Q to inputs of P and give us a pattern of connections. And this is this internal home. And PQ coalgebra is a category in itself in which each object is a state with a rule that associates the corresponding output of this internal home, updating the state according to the outcome. So if we consider an org-enriched category, we have to each object of the category we want to create associated to a polynomial. And for objects A1, AN, B, we will have the coalgebra on this internal home. And this will be the states we call in this way. And morphisms will be such that the objects have to satisfy two consistency conditions called the identitor and compositor. Sorry for being loose in this, but the idea is clear what it means. So the question is, what should be the objects in the org-enriched category I am thinking of? And I think that the objects defined as games are the best candidates. And the reason for this is that each local problem can be seen as a game by a single individual with the utility function in that game, in that local problem, with the outcomes in that problem, and the strategies will be the choices that have to be made. So we can see each individual decision making as a game, but then we have to associate a polynomial functor to each game. And the question is that I think that in this polynomial functor, the strategy profiles should be the inputs and the payoffs the outputs. What's the term? The directions and the positions, right? And I think that in that language provides us the possibility of connecting two games in such way that the state in the coalgebra of the home, internal home, will allow us to change the values of the payoffs. And since the payoffs change also the incentives for one equilibrium to another. But this is just pure speculation. I haven't written this down precisely, but I think that captures nicely what I have in mind, that interaction should be dynamic, that should change the participants in the interaction. And so my conclusion is that the properties of an enriched category of games deserve to be explored, and I know that you started to doing that. If you don't mind, I will try to do that in my framework, and we can compare notes later. But the possibility of rewiring the connections makes this representation much more realistic than the previous one, the traditional views in economics. But the question is that, going back to our Star Trek notion, resistance is futile to the possibility of having uncertainty and imprecision, right? Thank you. Thank you. So, sorry for being so fast and going over such amount of ugly notation, but I hope the core idea was clear.
I definitely think so. Given it's just the three of us, why don't we thank Fernando again and then ask more questions offline.
Thank you. Thank you.